Imagine standing under a night sky, gazing up at the stars, when suddenly silence shatters. A distant star doesn't just flicker or fade, it screams, not with sound, but with a pulse of energy so violent it bends the fabric of space itself. This isn't science fiction. It's a starquake, a cosmic tantrum where entire stars convulse, sending shockwaves across the universe. What if I told you that these celestial screams, these starquakes, are some of the most violent and mysterious events in the cosmos? They're not just ripples on a star's surface, they're earthquakes in the sky, so powerful they can distort space-time, rewrite magnetic fields, and even help us uncover the secrets of matter itself. Think about the last time you felt an earthquake, the ground trembling beneath your feet, a force so raw it reminds you how small we really are. Now picture that same power, but magnified 1 billion times, erupting from a star hundreds of light years away. These aren't quiet cosmic whispers, they're explosions of energy so intense they can outshine entire galaxies for a split second. And here's the wildest part, we're only just beginning to understand them. What triggers these stellar screams? Why do some stars shudder violently while others stay eerily still? And what can these cosmic convulsions teach us about the life and death of the universe's most brilliant giants? That's the journey we're taking today, into the heart of starquakes, where the laws of physics twist into something extraordinary. We'll dive deep into the science of how stars tremble, how astronomers listen to their vibrations like cosmic detectives, and why these events might hold the key to some of the universe's biggest mysteries. From neutron stars cracking under their own gravity to supermassive monsters unleashing bursts of energy that ripple across eternity, this is the story of stars that don't just shine but scream. Buckle up, the cosmos is about to get loud. To understand starquakes, picture our own planet during an earthquake. The ground shifts, plates grind together, and energy ripples outward. Now take that same violent motion, but instead of rock, imagine it happening across the unimaginably dense crust of a star, where a teaspoon of material could weigh as much as a mountain. That's a starquake, a seismic wave ripping through a star's surface or interior, shaking it with enough force to make entire planets tremble by comparison. But what triggers these cosmic tremors? Stars aren't static objects, they're dynamic, seething cauldrons of energy, and sometimes their own power turns against them. For some stars, especially ultra-dense neutron stars, it starts with the crust. These remnants of exploded stars are so compact that their outer layers freeze into a brittle shell, like a thin sheet of ice over a churning ocean. When internal pressures build, maybe from magnetic field shifts or the star's dizzying spin, that crust suddenly cracks, sending shock waves racing through the star's body. The energy released is staggering. A single starquake can unleash more power than billions of atomic bombs detonating at once, all in a fraction of a second. And then there are magnetic starquakes. Some stars, like magnetars, have magnetic fields trillions of times stronger than Earth's. These fields twist, snap, and rebind like cosmic rubber bands, releasing pent-up energy in violent spasms. When that happens, the star doesn't just shake, it screams across the electromagnetic spectrum, firing off X-rays and gamma rays so intense they can be detected thousands of light years away. Here's what makes them truly mind-bending. Unlike earthquakes, which fade into the ground, starquakes ripple through the very fabric of space-time itself. The energy distorts the star's gravitational field, sending tremors not just through matter, but through the universe's underlying structure. That's why astronomers listen so closely. These aren't just stellar tantrums. They're cosmic echoes, carrying secrets about how stars live, die, and warp reality around them. Stars don't just shake randomly. When starquakes hit, they vibrate in ways that reveal their deepest secrets, like a cosmic fingerprint. To understand how this works, picture throwing a pebble into a pond. The ripples spread outward in perfect circles, their patterns dictated by the water's properties, its depth, temperature, even the wind. Now replace the pond with a star and the pebble with a cataclysmic crack in its crust. The ripples become seismic waves racing through layers of plasma so hot and dense they defy imagination. But here's the twist: unlike water, a star isn't uniform. It's a layered onion of boiling gases, superheated plasma, and in neutron stars a crust harder than diamond yet thinner than a razor's edge. These waves don't travel in straight lines. They bend, speed up, or slow down depending on what they're moving through. In a sun-like star, plasma churns like a turbulent ocean, absorbing and redirecting vibrations. But in a neutron star, the waves can ricochet off the core, bounce through the magnetic field, and even skid across the surface at fractions of light speed. It's like ringing a bell, but instead of metal, the bell is made of hyper-compressed star matter, and the sound it makes isn't just noise. It's a pulse of energy astronomers can detect across the galaxy. Magnetic fields turn these vibrations into something even wilder. Imagine stretching a rubber band until it snaps. Now picture that rubber band is a magnetic field 1 trillion times stronger than Earth's, wrapped around a star. When it cracks back into place, it doesn't just release energy. It twists the very fabric of the star's plasma, sending shockwaves spiraling like a cosmic tornado. These magnetic starquakes don't just shake the star, they light it up. Some unleash flares so powerful they briefly outshine entire galaxies, all because of vibrations rearranging the star's invisible magnetic skeleton. Density plays the final, critical role. A star's interior isn't just hot, it's packed tighter than anything we can replicate on Earth. In neutron stars, matter is so dense that atoms collapse into a sea of neutrons with a crust that's both brittle and unbelievably strong. When a starquake cracks that crust, the vibrations don't just travel, they amplify, squeezing through layers where a sugar cube-sized chunk weighs as much as a mountain. That's why some starquakes can distort space-time itself. The energy is so concentrated, it doesn't just move through the star, it warps the universe around it. This is how astronomers listen to stars, by tracking these vibrations, whether through X-ray pulses, gamma-ray bursts, or ripples in space-time. They decode the star's hidden structure. Like geologists using earthquakes to map Earth's core, scientists use starquakes to peer into places no telescope can reach. Every tremor is a message written in the language of physics, screaming across the cosmos. And the louder the universe gets, the more we realize these aren't just explosions, they're textbooks written in fire waiting to be read. Not all stars scream equally. Some barely whisper, while others unleash cosmic howls that ripple across galaxies. The loudest, most violent starquakes come from stars living on the edge: neutron stars, magnetars, and pulsars, where the laws of physics are pushed to their breaking point. Take neutron stars first. These are the collapsed cores of once massive stars, squeezed so tightly by gravity that protons and electrons fuse into neutrons. The result, a city-sized object with the mass of our entire sun, spinning hundreds of times per second. Their crusts, only a few hundred meters thick, are under unimaginable strain. Picture an eggshell stretched over a bowling ball, then spun at dizzying speeds. It's no surprise these stars crack under the pressure. When they do, the quakes can release more energy in a millisecond than the sun emits in 100,000 years. Then there are magnetars, neutron stars turned up to 11. Their magnetic fields are so intense they could strip the atoms right out of your body from halfway across the galaxy. These fields don't just sit there, they twist, snap, and reboot like cosmic power lines in a hurricane. When a magnetar's crust shifts, the magnetic energy doesn't just shake the star, it supercharges the quake, turning it into an X-ray tsunami. Some of the brightest flashes ever detected in space, those are magnetars screaming as their crusts shatter under magnetic torment. Pulsars, the universe's lighthouses, have their own quake stories. These rapidly spinning neutron stars beam radiation across space with eerie precision until a starquake throws them off rhythm. A single crustal shift can speed up a pulsar's spin mid-rotation, like a figure skater pulling in their arms unexpectedly. Astronomers call these events glitches, but that word doesn't capture the violent, sudden, seismic adjustments that rewrite the star's rotation in an instant. Now compare that to our Sun. Its sunquakes are gentle ripples, in comparison more like a drumhead vibrating than a crust shattering. When solar flares erupt, they send shockwaves through the Sun's plasma, creating patterns we can observe as subtle, ringing oscillations. But these are surface-level murmurs, not the deep, structural quakes that twist neutron stars. The Sun is a placid lake, magnetars are oceans in a hurricane. Why the difference? It all comes down to density and magnetic fury. Ordinary stars like the Sun are gaseous, their energy diffusing smoothly. But in neutron stars and magnetars, matter is packed so tightly that stress has no escape valve. Crusts crack, magnetic fields erupt, and the star's entire structure convulses, sending screams of energy, light, and gravitational waves echoing through the cosmos. These aren't just stars trembling, they're stars tearing themselves apart, revealing physics we can't recreate anywhere else in the universe. Magnetars are the universe's ultimate cosmic rebels. Stars so volatile, so magnetically charged, they rewrite the rules of physics. Imagine a magnetic field so powerful it could erase your credit card from halfway across the galaxy. Now multiply that by 1 trillion, that's a magnetar. These aren't just stars with strong magnetic fields, they're monsters twisting space-time itself into knots, and when their patience snaps, so does their crust. The result, starquakes that don't just tremble, they detonate. What makes magnetars different? It's all in the magnetic chaos. While regular neutron stars spin fast, magnetars take it further, with magnetic fields so intense they act like cosmic prisons. Picture a rubber band stretched to its limit, except this one's made of pure magnetic energy, wrapped around a star 20 times tighter. The tension builds until snap, the star's crust fractures under the strain. But here's where it gets wild. When a magnetar's crust cracks, it doesn't just release seismic energy. It unleashes a magnetic explosion so bright, it can outshine every star in the Milky Way combined for a fraction of a second. These eruptions, called giant flares, are the universe's most violent tantrums. In 2004, a magnetar halfway across the galaxy fired off a flare so powerful it briefly ionized Earth's upper atmosphere from 50,000 light-years away. That's like a campfire singeing your eyebrows from another continent. And the energy, it's not just light or heat. Magnetar flares punch through space-time, emitting X-rays and gamma rays in pulses so precise, they're like cosmic Morse code, if Morse code could vaporize planets. But why so much destruction? The answer lies in the star's magnetic skeleton. Unlike Earth's stable field, a magnetar's field is like a tangled ball of live wires. As the star spins, those wires twist tighter and tighter until pop, they snap back into place, whipping the star's surface with enough force to crack it open. The energy doesn't just ripple outward, it rebounds, bouncing between the star's crust and magnetic field like a pinball of pure violence. And here's the eerie part, we can hear them. Not with our ears, but with telescopes tuned to X-rays and gamma rays. Each flare carries a distinct echo, a vibration pattern that reveals the star's hidden structure. It's like listening to a bell ring, except the bell is a dying star, and the sound is a scream written in radiation. Magnetars are cosmic time bombs ticking away in the void. Some quiet down after a few thousand years, others keep erupting, their magnetic fields refusing to settle. But one thing's certain, when a magnetar screams, the universe listens. And for astronomers, that scream isn't just noise. It's a treasure map leading us closer to understanding the most extreme physics the cosmos has to offer. Pulsars are the universe's metronomes, cosmic clocks spinning with such precision. Their rhythmic pulses can rival atomic timekeeping, but sometimes without warning that steady beat stutters. The star's spin lurches forward, speeding up in a fraction of a second as if something deep inside has snapped. Astronomers call these events glitches, but that bland term hides the truth. These are starquakes in action, seismic spasms so powerful they rewrite a pulsar's rotation mid-heartbeat. To grasp how this works, picture a figure skater spinning with arms outstretched. As they pull their arms in, they spin faster, conserving angular momentum. Now replace the skater with a city-sized neutron star, spinning hundreds of times per second with a crust denser than diamond. When a starquake fractures that crust even slightly, the star's interior shifts. Superfluid neutrons in its core, normally frictionless, suddenly latch onto the crust like a clutch engaging. The result, a sudden speed boost, as if the skater's arms were yanked inward by an invisible force. The numbers defy intuition. In 2019, astronomers watched a pulsar named Vela 1100 light-years away jolt forward, gaining an extra 2 revolutions per minute in less than a second. That might sound tiny, but for an object with the sun's mass spinning 10 times faster than a kitchen blender, it's like a freight train accelerating instantly without engine power. The energy required, equivalent to a magnitude 23 earthquake, if such a thing could even exist on Earth. Glitches aren't random. They're seismic fingerprints, hinting at layers of quantum strangeness inside these stars. Between the brittle crust and the chaotic core lies a zone of superfluid neutrons, flowing without resistance until a quake disrupts the delicate balance. Some theories suggest vortices in this superfluid suddenly unpin, transferring energy outward like a whip cracking. Others propose avalanches of crustal fractures, tiny at first, then cascading into a system-wide slip. What's undeniable is the aftermath. After a glitch, some pulsars heal, their spins gradually returning to normal as internal forces rebalance. Others remain forever altered, their rhythms broken by the quake's violence. And every hiccup, every speed up is a message, a clue about the extreme physics governing matter crammed into such impossible density. These tremors do more than disrupt spin. They send vibrations ringing through the pulsar's magnetic field, sometimes twisting it into knots that unleash bursts of X-rays or radio waves. It's as if the star's entire structure briefly convulses, recalibrating itself in real time. For astronomers, that's the gift of glitches, a fleeting chance to peer inside a pulsar's hidden machinery where matter doesn't behave like anything we know. Each quake is a probe, shaking loose secrets from a place where the rules of reality are written in gravity's boldest strokes. Detecting starquakes isn't as simple as pointing a telescope at the sky and waiting for a cosmic shudder. These violent events hide in plain sight, masked by distance and the very nature of the energy they release. But astronomers have a toolkit of high-tech instruments designed to capture these stellar screams, each one tuned to a different wavelength of cosmic chaos. X-ray telescopes are the frontline detectives for starquake hunting. When a neutron star's crust fractures or a magnetar's magnetic field snaps, the energy often erupts as X-rays, invisible to our eyes but blazingly bright in the high-energy universe. NASA NICER, an instrument mounted on the International Space Station, is built precisely for this. It doesn't just see X-rays, it times them with the precision of an atomic clock, catching the millisecond flickers of a starquake's aftermath. Imagine listening to a heartbeat, except the heart is a city-sized star, and every irregular pulse could mean its crust just cracked under unimaginable pressure. Gamma-ray observatories like Fermi take it further. Some starquakes don't stop at X-rays, they unleash gamma-ray bursts, the most energetic explosions since the Big Bang. These aren't gentle ripples, they're full-throated roars, packing more power in a single second than the sun will emit in its entire lifetime. When Fermi detects a sudden gamma-ray spike from a known magnetar, it's often the smoking gun of a starquake, magnetic field lines breaking and reconnecting like cosmic whips, supercharging the star's cry into a gamma-ray howl. But light isn't the only messenger. Gravitational wave detectors like LIGO and Virgo listen for the faint tremors in spacetime itself. While most starquakes are too subtle for current detectors to pick up, theoretical models suggest the most violent fractures, especially in rapidly spinning neutron stars, could warp spacetime enough to send ripples across the galaxy. It's like feeling an earthquake through your feet before you hear the rumble, except the ground is the fabric of reality. Then there's radio astronomy. Pulsars, the lighthouse remnants of dead stars, beam radio waves with metronomic precision until a starquake glitches their spin. Radio telescopes catch these hiccups, tracking changes in pulse timing down to nanoseconds. A sudden speed-up might mean the star's crust just slipped, transferring momentum from its superfluid core like a car's wheel spinning on ice before gripping the road. The real magic happens when these tools work together. In 2020, a Magnetar named SGR 1935 plus 215 went silent in X-rays, then screamed in gamma rays hours later. Telescopes across the spectrum traced the aftermath, piecing together a story of crustal fractures and magnetic reconnections like forensic scientists at a cosmic crime scene. Each wavelength reveals a different layer of the chaos, proving that to study starquakes, you don't just watch the stars. You listen, measure, and wait for the moment the universe decides to reveal its secrets. Starquakes don't just send shockwaves through space, they sing. Not in the way you might think, with actual sound traveling through the vacuum, but in vibrations so precise that scientists can translate them into something our ears can understand. Imagine taking the raw energy of a star's convulsions, a crack in its crust, a snap of its magnetic field, and turning it into a deep, resonant hum or a piercing cosmic shriek. This isn't just artistic interpretation. It's real science, a way to hear the universe in a language beyond light. The process starts with data, waves of X-rays, gamma rays, or gravitational disturbances captured by telescopes. These signals arrive as jagged lines on a graph, spikes and dips representing the star's furious energy. But here's where it gets creative. Scientists sonify these signals, assigning pitches and rhythms to the raw numbers. A sudden spike in X-rays might become a sharp, metallic ping. A slower, rolling vibration from a neutron star's crust could morph into a bass, heavy drone, like a cello played at the bottom of the ocean. The result, a symphony of stellar violence where every quake has its own eerie voice. Some starquakes sound almost musical. Take magnetars. Their magnetic field ruptures produce rapid, staccato bursts of X-rays that, when sonified, resemble the plucked strings of a harp if that harp were strung with lightning. Others, like the slow, grinding quakes of older neutron stars, translate into deep, ominous tones, like a subwoofer tuned to the frequency of a black hole. And occasionally, when a star's crust fractures in a way that sends vibrations bouncing between its core and surface, the sound loops back on itself, creating an unearthly echo, as if the star is singing in rounds. But why bother turning data into sound? Because our ears detect patterns our eyes might miss. A subtle shift in a starquake's pitch could reveal a hidden layer in the star's structure, like a geologist listening for hollow spaces in rock. A sudden crescendo might expose a magnetic reconnection event where field lines snap and reboot like live wires. It's not just about making space pretty. It's about hacking our own biology to understand the cosmos in a new way. Close your eyes for a moment. Picture a magnetar, its surface splitting under magnetic strain, and instead of silence, you hear a metallic screech, like nails on a chalkboard, if the chalkboard were light years wide and forged from dying star matter. That's the sound of spacetime itself being twisted, a scream filtered through mathematics into something human. It's haunting, beautiful, and undeniably alien, a reminder that the universe isn't just something we see. It's something we can feel, vibrating through us in frequencies older than time. A magnitude 9 earthquake on Earth can rip continents apart, flatten cities, and shift the planet's axis by inches. But in the cosmic arena, that's barely a whisper compared to the raw, unfiltered violence of a starquake. Imagine packing the energy of every earthquake in recorded history, every tremor, every tsunami, every tectonic scream, into a single millisecond. Now multiply that by 1,000,000,000. That's the scale we're dealing with when a neutron star's crust shatters. Let's put numbers to the chaos. Earth's most powerful earthquake, the 1960 Chile quake, hit magnitude 9.5, releasing roughly enough energy to power human civilization for 200 years. A starquake on a magnetar, even a modest one, can unleash the equivalent of a magnitude 20 earthquake. That's not just an incremental jump, it's a vertical leap into pure destruction. The energy difference between a magnitude 9 and a magnitude 20 quake isn't linear, it's exponential. Each single-digit increase on the scale represents a 32-fold multiplication in energy. So while a magnitude 9 quake might release enough energy to power a small country for a year, a magnitude 20 starquake could power a galaxy. Here's another way to picture it. If the Hiroshima atomic bomb released enough energy to boil a swimming pool's worth of water, a typical starquake could vaporize every ocean on Earth instantly. The most extreme magnetar flares, they outshine our entire sun for a fraction of a second by a factor of 100 quadrillion. That's a 1 followed by 17 zeros. To human senses, these numbers are meaningless abstractions, but translated into force, they mean a starquake doesn't just shake a star, it rewires it. Earthquakes fade because our planet's crust absorbs and dissipates energy, but a neutron star's crust is so dense, so rigid, that quakes don't dissipate, they amplify. Vibrations ricochet through the star's interior at nearly light speed, bouncing between the crust and core like echoes in a steel cathedral. And because neutron stars are so small, just 12 miles across, the energy has nowhere to go but back into the system, building wave upon wave until the star rings like a struck bell. The aftermath is even more alien. On Earth, quakes leave fault lines and rubble. On a magnetar, they leave scars of twisted magnetic fields and X-ray afterglows visible for light years. Some starquakes even trigger cascading failures like a domino effect where one fracture leads to another, until the star's entire surface is a web of cracks under unimaginable strain. Yet for all their fury, starquakes aren't random. They follow laws, just laws written in extremes we're only beginning to decode. Each one is a laboratory for physics that doesn't exist anywhere else. Matter crushed to breaking point, magnetic fields strong enough to bend atoms, and energy densities that flirt with the limits of reality itself. Compared to that, even Earth's mightiest quakes feel like the faintest sigh. The night of December 27, 2004, started like any other for astronomers until a blast of gamma rays lit up detectors across the solar system. The source, a magnetar named SGR 180620, 50,000 light-years away in our galaxy's far reaches. In just 0.1 seconds, it unleashed a flare with the energy of 500,000 suns, more power than our star will radiate in its entire lifetime. To this day, it remains the brightest starquake ever recorded, a cosmic detonation so fierce it temporarily ionized Earth's upper atmosphere, disrupting radio communications worldwide. This wasn't just a brilliant flash. The event peeled back the curtain on starquakes' true potential. Scientists had theorized about magnetar eruptions for decades, but SGR 180620 proved they could dwarf anything in our models. The flare's afterglow lingered for minutes, flickering with tiny oscillations like a ringing bell's echoes, that revealed the star's crust had fractured globally. Imagine cracking an egg, except the shell is a neutron star's surface, and the crack unleashes enough energy to vaporize every planet in our solar system 1,000 times over. But SGR 180620 wasn't the first starquake to rewrite astronomy textbooks. Decades earlier, in 1979, another magnetar, SGR 0526, startled scientists with a gamma ray burst so intense it saturated detectors designed to monitor nuclear bomb tests. At first, researchers thought it might be a nearby supernova. Then the pulsars came. Rhythmic X-ray beats every 8 seconds, the unmistakable signature of a spinning, quaking neutron star. This was the moment astronomers realized some stars don't just explode, they convulse, their rigid crust splitting under magnetic strain like frozen lakes in a heat wave. Fast forward to 2007 when NASA, a Swift satellite, caught a magnetar in the act. SGR 0501 plus 4516 emitted a series of X-ray screams, each burst preceded by subtle vibrations in the star's crust like foreshocks before a megaquake. For the first time, scientists saw the chain reaction, magnetic fields twisting until they snapped, triggering crustal fractures that then amplified the energy release. It was a stellar Rube Goldberg machine where each step, twist, crack, detonate unfolded in milliseconds. What makes these events so revolutionary isn't just their violence. It's what they've taught us about matter itself. The vibrations from SGR 180620's quake, for example, confirmed neutron star crusts are 10 billion times stronger than steel, yet still brittle enough to shatter under magnetic pressure. And the afterglows, they've revealed neutron stars may have mountains not of rock but of ultra-dense matter, towering mere centimeters high yet weighing more than Mount Everest. Every recorded starquake is a time capsule, preserving snapshots of physics pushed to extremes we can't recreate on Earth. From the 1979 wake-up call to the 2020 discovery of a magnetar hiccuping in our galactic backyard, each event peels back another layer of these cosmic enigmas. They're not just explosions, they're messages written in gamma rays, X-rays, and space-time ripples telling us how stars live, die, and sometimes scream themselves apart. Starquakes aren't just violent events, they're cosmic sculptors carving stars into entirely new shapes over millennia. Take neutron stars, for example. These ultra-dense remnants are born from supernova, but it's the relentless tremors that truly shape their destiny. Every time the crust fractures, it's not just releasing energy, it's rearranging the star's very skeleton. Picture a blacksmith hammering hot metal, each strike forging a stronger, stranger form. Now replace the hammer with gravity and magnetic fields and the metal with a star's crust. That's stellar evolution in action. One of the most dramatic transformations happens in magnetars. Their magnetic fields are so intense, they literally twist the star's surface like taffy. When a starquake cracks the crust, those fields snap into new configurations, sometimes straightening, sometimes tangling further. It's like rewiring a live electrical grid while it's still powered on. Over centuries, these repeated quakes and magnetic shifts can turn a magnetar's exterior into a patchwork of scars, where fractures heal only to rupture again under fresh strain. Some models suggest this cycle might even slow a magnetar's spin over time, as energy bleeds away in seismic spasms and magnetic fireworks. Then there's the matter hiding beneath the surface. Neutron stars are thought to have cores of exotic matter, possibly quark-gluon plasma, a state so extreme it hasn't existed naturally since the universe's first microseconds. Starquakes might be our only window into this alien realm. When a quake shakes a neutron star deep enough, the vibrations could briefly unzip the crust, exposing glimpses of this primordial soup. It's akin to geologists discovering magma by studying earthquakes, except here, the magma is a fluid of fundamental particles, and the earthquake could outshine a supernova. These tremors don't just reveal hidden layers, they can also alter a star's fate. Pulsars, for instance, rely on precise spin to beam their lighthouse-like signals across space. A major starquake can disrupt that rhythm, either by speeding up the rotation as crustal shifts transfer momentum from the core, or by warping the magnetic field lines that channel those beams. Some pulsars die temporarily after quakes, their radio signals vanishing for months until the star's interior settles. Others awaken after decades of silence, jolted back to life by a fresh fracture. Perhaps most intriguing is how starquakes might influence stellar corpses over cosmic timescales. A neutron star's crust isn't infinitely durable. Repeated quakes could, theoretically, fragment it entirely, leaving behind a bizarre quark star, an object even denser and more enigmatic. Alternatively, the cumulative energy of countless starquakes might push some magnetars over a critical threshold, triggering a final, cataclysmic collapse into a black hole. What's certain is this: starquakes aren't footnotes in a star's life. They're turning points, moments when gravity, magnetism, and quantum physics collide to rewrite a celestial object story. Every crack in a star's crust isn't just destruction, it's evolution at work, reshaping the universe one seismic scream at a time. When a starquake rips through a neutron star, the energy doesn't just vanish into the void, it lingers, reverberating through the fabric of space-time itself. These aren't just seismic waves confined to the star's crust. They're cosmic shock waves, powerful enough to warp the universe's very structure, sending ripples outward at the speed of light. This is where starquakes collide with one of the most revolutionary fields in modern astronomy: gravitational wave detection. Think of space-time as a taut trampoline. Drop a bowling ball onto it and the fabric dips and trembles. Now replace the bowling ball with a neutron star convulsing from a magnitude 20 starquake. The distortion isn't just deeper, it's violent, sending waves cascading across the trampoline's surface. Gravitational waves are those ripples minus the trampoline. They're literal stretches and compressions of reality, born from the most energetic events in the cosmos, colliding black holes, merging neutron stars, and perhaps starquakes. Here's why that matters. Gravitational wave observatories like LIGO and Virgo are designed to catch these ripples. Their laser-split arms act as cosmic rulers, measuring distortions smaller than an atom's width. So far, most detections have come from black hole mergers, events so cataclysmic they briefly outshine entire galaxies. But theorists suspect starquakes could produce their own gravitational fingerprints, especially in hyper-dense neutron stars. When a magnetar's crust fractures or a pulsar's spin glitches, the energy release isn't just electromagnetic. It's mechanical, shaking the star's very mass, and mass, as Einstein taught us, warps spacetime. The challenge is intensity. A typical starquake might release 1 billion times the energy of Earth's strongest earthquake, but neutron stars are tiny, just 12 miles across. Their gravitational waves are whispers compared to black hole collisions, yet some models predict that under the right conditions, like a starquake triggering a cascade of crustal failures, the resulting waves could be just loud enough for future detectors. Imagine a bell ringing in a hurricane. Today's instruments might miss it, but next-generation observatories like the planned Cosmic Explorer or Einstein telescope could be sensitive enough to hear. There's tantalizing indirect evidence already. In 2007, a Magnetar starquake was so powerful it altered the star's spin and emitted a pulse of gamma rays. Astronomers later calculated that if even a fraction of that energy went into gravitational waves, it should have been detectable had LIGO been online at the time. Then there's the mystery of continuous waves. Some neutron stars may hum at near-constant frequencies, their steady vibrations fueled by quakes or magnetic shifts, theorized to produce gravitational waves too faint for current tech but potentially within reach of upgrades. What would detecting a starquake's gravitational waves tell us? For starters, the star's interior. Seismic waves on Earth let geologists map our planet's core. Gravitational waves from starquakes would do the same for neutron stars, revealing whether their cores are soup-like fluids, crystalline solids, or something stranger. The waves could also expose cracks in Einstein's relativity. In extreme gravity fields, tiny deviations from predicted wave patterns might hint at new physics, clues to theories like quantum gravity or extra dimensions. For now, it's a waiting game. Every magnetar flare, every pulsar glitch is a potential gravitational wave source. And when detectors finally catch that first starquake ripple, it won't just be a new signal. It'll be a new language, one where stars don't just scream in light, but in the very bends and folds of the universe. What actually causes a star to scream? The answer isn't simple, because beneath the surface of a neutron star, physics warps into something unrecognizable. Some scientists argue starquakes begin with magnetic fury, where field lines stretched beyond their limits suddenly snap like over-tightened guitar strings. Others point to the star's crust, an ultra-dense shell under such unimaginable strain that even a minor shift can trigger a seismic chain reaction. And then there's the wild card, star tsunamis, where internal waves crash against the crust with enough force to fracture it from within. Take the magnetic snapshot theory first. Magnetars with fields a trillion times Earth's are prime suspects. Their magnetic fields aren't static. They're dynamic, twisting and braiding like live wires in a storm. When these fields twist too far, they recoil violently, releasing energy that cracks the star's crust like a whip striking glass. This isn't just theoretical. In 2007, NASA, a Swift satellite, caught a magnetar mid-quake, its X-ray emissions flaring in perfect sync with models of magnetic reconnection. A eureka, a moment that suggested the star's skeleton of magnetic force had abruptly rearranged itself. But magnetism isn't the only culprit. Neutron star crusts, though only a few hundred meters thick, endure pressures so extreme that atomic nuclei compress into bizarre shapes, rods, slabs, even nuclear pasta. This crust isn't uniform. It's riddled with defects, like a diamond with invisible fractures. When stress builds, whether from the star's spin slowing over centuries or sudden shifts in its superfluid core, these defects give way catastrophically. Picture leaning on a table covered in fine china. At first, nothing happens until one plate shifts and the entire stack collapses in a domino effect. That's a crustal starquake, tiny breaks amplifying into a system-wide failure. Then there's the star tsunami hypothesis. Some models suggest neutron stars might harbor internal waves, not of water, but of superfluid neutrons sloshing against the crust. Normally, this motion is smooth, frictionless, but if the core's rotation slows even slightly, these waves can pile up like ocean breakers hitting a seawall. The resulting impact might not just crack the crust, it could launch fragments of it into space, a phenomenon astronomers poetically call neutron star avalanches. The real debate, though, isn't just about how starquakes start, it's about where. Are they skin deep, confined to the crust, or do they rumble up from the core where matter exists in states beyond our current physics? The answer might be both. Smaller quakes, like those causing pulsar glitches, could be crustal, mere surface trembles, but the monster flares from magnetars, those might tap into the core's energy, where magnetic fields intertwine with quantum vortices in the superfluid. It's like comparing a twig snapping to a volcano erupting, same planet, vastly different depths. What's fascinating is how these theories aren't mutually exclusive. A magnetic snap might weaken the crust, priming it for a tsunami's strike, or a deep core shift could send tremors upward, fracturing the surface like ice under a hammer. Every detected starquake adds clues, but the truth is kaleidoscopic. The triggers are as layered and violent as the stars themselves, and until we catch one in the act, from crust to core, the debate will rage as fiercely as the quakes themselves. When a magnetar screams, the universe doesn't just listen, it recoils. These aren't ordinary stellar temper tantrums. The most violent starquakes can ignite short gamma-ray bursts, the cosmos equivalent of detonating a nuclear bomb in every square inch of space simultaneously. These GRBs outshine entire galaxies in less time than it takes to blink, packing more energy into milliseconds than our sun will emit in 10 billion years. And in rare, terrifying cases, the source isn't a colliding star or black hole. It's a magnetar tearing itself apart from the inside out. Picture this: a magnetar's crust fractures under magnetic strain, but instead of settling, the rupture triggers a runaway reaction. The break exposes the star's interior magnetic field, which snaps back with the force of 1 billion lightning strikes. This recoil launches a jet of plasma and radiation at 99.9% light speed, focused into a beam narrower than a pencil but hotter than a supernova's core. That beam is a gamma-ray burst, a death ray spanning light years, capable of stripping atmospheres from planets halfway across the galaxy. Earth got grazed by one in 2008, a burst from 2.5 billion light-years away that still briefly outshone the full moon. The sterilization range of these events chills the blood. A Magnetar quake emitting a GRB within 10 light-years would bathe our solar system in enough X-rays and gamma rays to obliterate ozone layers, ignite global wildfires, and irradiate surface life into extinction. The fossil record hints this might have happened before a mass extinction 450 million years ago aligns suspiciously with a suspected nearby GRB. And while Milky Way magnetars are thankfully rare, we know of about 30. A close-range burst wouldn't announce itself with warning tremors. The first sign would be a blue-white flash in the sky, followed by planetary ecological collapse within days. Yet paradoxically, these same apocalyptic forces might seed new beginnings. Some theorists suggest GRBs from Starquakes could forge heavy elements like gold and platinum in their wake, scattering them across galaxies. The very events that sterilize worlds might also plant the ingredients for future planets and life. It's a brutal cosmic irony, destruction and creation bound together in the aftershocks of a screaming star. What stops every Magnetar quake from becoming a GRB? It comes down to geometry and energy thresholds. Most starquakes release their fury in all directions, like a shattered light bulb spraying glass. But when a quake channels its energy into twin jets, often along the star's rotational axis, the result is a gamma-ray blowtorch cutting through the cosmos. We've detected GRBs in distant galaxies that match this profile perfectly. Brief, intensely focused, and trailing X-ray afterglows that fingerprint magnetar involvement. The unsettling truth is that we're only seeing the tip of the iceberg. For every GRB we detect, countless others fire harmlessly into empty space or strike galaxies too distant for our telescopes. The universe may be crisscrossed with these lethal beams, silent and invisible until they intersect something or someone. It's a reminder that starquakes aren't just stellar curiosities. They're cosmic gunshots in the dark, and we're only beginning to learn how to dodge them. Starquakes have torn their way from astrophysics papers straight into our wildest sci-fi nightmares, and for good reason. When Doctor Who featured a magnetic star convulsing in the episode The Impossible Planet, it wasn't just spectacle. The scriptwriters tapped into real science, painting a Magnetar's quake as a universe-shaking event that could unravel spacetime. Sure, the TARDIS team's dramatic escape bends reality. Real starquakes don't open interdimensional rifts, but the core fear is legit. A Magnetar's eruption really could scorch planets light years away. Then there's Interstellar, where the crew navigates a neutron star's gravitational waves. While the film swaps starquakes for black hole theatrics, the vibe is eerily accurate. Neutron stars do warp spacetime when they shudder, and a quake's energy could ripple outward like the movie's tidal waves, just minus Matthew McConaughey's tears. The science gets hazy when characters survive a close-range pulse, though. In reality, the radiation from even a modest starquake would vaporize a spacecraft before the crew could whisper, "Murph." But sci-fi's most delicious exaggeration, Star Trek's Pulsar earthquakes. In one episode, the Enterprise dodges crust fragments from a cracking neutron star like cosmic shrapnel. Playfully absurd, neutron star material weighs 1 billion tons per teaspoon, so a pebble-sized chunk would punch through shields like tissue paper. But the visual nails a truth. Starquakes do hurl debris, just at speeds that'd make photon torpedoes look slow-mo. Where fiction thrives is in the stakes. Books like Alastair Reynolds' Revelation Space depict starquakes as apocalyptic triggers, unleashing gamma-ray bursts that sterilize star systems. Grim, absolutely, plausible, frighteningly so. The irony: these stories often undersell the violence. A real Magnetar flare could outshine the Milky Way, while sci-fi tends to opt for flashy sound effects over the silent, lethal reality of X-ray suffocation. Yet inaccuracies aren't failures, they're invitations. When The Expanse shows a belter colony panicking over a star shudder, it doesn't matter that the physics is fuzzy. What sticks is the primal terror. Stars scream, and sometimes the universe screams back. Science fiction's job isn't to recite textbooks. It's to make us feel the quake in our bones, even if the equations get left in the dust. And in that, Hollywood's stellar tantrums nail the assignment. Our sun may seem like a calm, steady ball of light compared to the violent tantrums of magnetars, but don't be fooled. It has quakes of its own, they're just different. Imagine comparing a toddler's tantrum to a volcanic eruption. Both are outbursts, but one shakes the room while the other reshapes continents. Solar quakes, or sunquakes, release energy equivalent to millions of hydrogen bombs, yet on the cosmic scale, that's barely a hiccup. Here's why the sun gets off easy. Unlike neutron stars, which are hyper-dense skeletons of dead stars, our sun is a churning plasma ball with no solid crust to crack. Its quakes aren't fractures but pressure waves rippling through its gaseous layers, like sound echoing through a foggy canyon. When a solar flare erupts, the explosion slams into the sun's surface, sending vibrations deep into its interior. These waves bounce around, creating patterns that scientists can map, like sonar pinging through an ocean of fire. This process, called heliosismology, turns the sun into a giant musical instrument. By tracking how these waves move, astronomers can peer inside the sun the way doctors use ultrasound to see unborn babies. The waves speed up or slow down depending on the temperature and density of the plasma they pass through, revealing hidden jet streams, rotating layers, and even the sun's core, a place sunlight takes 100,000 years to escape from. But don't mistake gentler for unimportant. Sunquakes teach us how stars work. In 2011, a solar flare triggered a sunquake so powerful it sent seismic waves racing across the sun's surface at 250,000 miles per hour. The resulting ripples lasted for hours, giving scientists a front-row seat to stellar acoustics. Compare that to a neutron star's quake, where the vibrations last milliseconds and vanish into space-time. Sunquakes are the slow, detailed symphony to Magnetar's death metal scream. Could our sun ever unleash something truly catastrophic? Almost certainly not. It lacks the two ingredients that make neutron star quakes so terrifying: unimaginable density and magnetic fields strong enough to distort atoms. The sun's magnetic fields, while fierce by Earth standards, are 1,000,000 times weaker than a magnetar's. And without a solid crust to fracture, the worst it can do is belch plasma in our direction, disrupting satellites maybe, but not cracking space-time. Yet in a way, that's what makes sunquakes so special. They're a reminder that even the quiet stars are shouting secrets. We just have to learn how to listen. Every ripple, every reverberation is a clue, not just about our sun, but about every star in the sky. And unlike their neutron star cousins, we can study these quakes up close without waiting for a gamma-ray blast to light the way. The sun isn't just our nearest star, it's a cosmic laboratory trembling with lessons. Even with all we've learned about starquakes, some mysteries refuse to crack. Take periodicity. Why do some neutron stars shudder like clockwork, while others erupt at random? Magnetar SGR 0501 plus 4516, for instance, fired off bursts every 34 days like cosmic hiccups for years, then suddenly fell silent. Meanwhile, its cousin SGR 1935 plus 215 screams unpredictably, with years of calm shattered by violent spasms. Is it a difference in magnetic field structure? Crustal density, or something deeper buried in the quantum soup of their cores. Then there's the quark star conundrum. These theoretical objects, even denser than neutron stars, might exist in a state where protons and neutrons dissolve into free quarks. If real, their starquakes wouldn't just crack crusts. They'd fracture the very fabric of quark matter itself, releasing energy in ways we can barely model. Picture an earthquake where the ground isn't rock, but a sea of unchained particles bound by forces stronger than anything in nature. Some simulations suggest quark starquakes could produce gravitational waves with unique harmonics, low, resonant warbles unlike the sharp chirps of neutron stars. But without a confirmed quark star to observe, it's like trying to study hurricanes by only reading ancient sailors' logs. The strangest puzzle might be silent starquakes. A handful of neutron stars show sudden spin changes, glitches or anti-glitches without any detectable X-ray or gamma-ray bursts. Where's the energy going? One theory points to dark fractures, quakes so deep they vibrate the star's core without reaching the surface, like a submarine earthquake that never triggers a tsunami. Others speculate the energy leaks out as dark matter or some exotic particle we can't yet detect. It's a cosmic magic trick where the evidence vanishes before our telescopes can blink. And what about hybrid stars? These speculative objects might have neutron star crusts shielding quark matter interiors. A quake on such a star could start with a crustal crack, then trigger a phase transition like ice melting, except the water is a quark gluon plasma. The result, a quake that begins as a tremor but escalates into a full-blown stellar metamorphosis, rewriting the star's fundamental composition in milliseconds. The biggest question remains, are we missing an entire class of starquakes? Current detectors focus on X-rays, gamma rays, and gravitational waves. But what if some quakes broadcast in neutrinos or distort spacetime in ways our instruments aren't calibrated to catch? Every unexplained pulsar glitch, every quiet magnetar flare could be a clue, a whisper of physics operating beyond the edges of our textbooks. Until we catch one in the act from crust to core, starquakes will keep their deepest secrets locked behind layers of hyper-dense matter and magnetic chaos. The stars aren't just screaming, they're speaking in riddles. The next decade could rewrite everything we know about starquakes, thanks to a new generation of telescopes built to eavesdrop on the universe's most violent tantrums. Leading the charge is the European Space Agency's Athena, slated to launch in the 2030s with X-ray vision so sharp it could spot a quake on a neutron star halfway across the observable universe. Unlike current instruments that catch starquakes by accident, like stumbling upon a scream in the dark, Athena will hunt them deliberately, its detectors fine-tuned to the faintest seismic whispers from magnetars and pulsars. Picture a microphone dropped into the heart of a hurricane, isolating individual raindrops. That's the precision we're talking about, except the raindrops are vibrations in a star's crust, and the hurricane is a magnetic field strong enough to atomize planets. Athena's secret weapon, its ability to dissect starquakes in real time. Current telescopes like NICER snap X-ray photos every few milliseconds, impressive, but still a flipbook compared to Athena's high-definition video. With resolution 100 times finer, it won't just see the explosion. It'll track the crack propagating through a neutron star's crust, measure how magnetic fields recoil from the rupture, and even catch the moment energy ricochets between the surface and core. For the first time, we'll witness starquakes unfold frame by frame, like watching slow-motion footage of a glass shattering. Except the glass is 1 trillion tons of hyper-dense matter, and the shatter bends spacetime itself. But Athena isn't flying solo. NASA proposed Lynx X-ray Observatory, if greenlit, could pair with it to create a cosmic surveillance network. Lynx's wider field of view would scan entire swaths of the sky, flagging starquakes for Athena to zoom in on, like a spotter guiding a sniper. Together, they'd catch quakes too subtle or distant for today's tech, potentially uncovering hidden populations of magnetars lurking in galactic backwaters. There's even talk of syncing these X-ray eyes with gravitational wave detectors like LIGO, creating a multi-messenger alert system. Imagine getting a gravitational tremor from Virgo while Athena's X-rays pinpoint the culprit. A neutron star's crust collapsing 40,000 light-years away, its death throws broadcast in both ripples and light. The real game-changer, these missions might finally answer whether starquakes can birth gravitational waves detectable from Earth. Current models are split. Some predict neutron star vibrations are too faint, while others argue crustal fractures could ring spacetime like a bell if conditions align. Athena and Lynx could settle the debate by identifying quakes with the perfect storm of energy and asymmetry, directing gravitational wave hunters where to listen. A single confirmed detection would crack open neutron star interiors like a cosmic walnut, revealing whether their cores are seas of free quarks, crystalline exotic matter, or something even stranger. Beyond brute force observation, these telescopes will test wild theories we can't probe any other way. Take strange star hypotheses, objects so dense, their quakes might emit strangelets, nuggets of quark matter that convert anything they touch. Or the idea that some gamma-ray bursts aren't from colliding stars, but from starquake storms where a magnetar's entire surface shatters in sequence. Athena's data could turn these sci-fi speculations into hard physics, or send theorists back to their chalkboards. The clock is ticking. Within our lifetime, these missions could transform starquakes from cosmic curiosities into universal diagnostics. Tools to weigh neutron star cores, map magnetic field geometries, and maybe even glimpse quantum gravity in action. Every shattered crust, every magnetic snap, every space-time tremor will become a clue in the grandest puzzle of all. What happens to matter when the universe crushes it beyond recognition? The stars have been screaming for billions of years. We're finally building the ears to hear them. Capturing the fury of a starquake on Earth sounds impossible until you step inside a plasma physics lab. Scientists can't replicate the crushing gravity of a neutron star, but they've found clever workarounds using machines that squeeze matter to extreme conditions. Take the Z machine at Sandia National Labs. This towering metallic beast generates pulses of 20 million amps, hotter than the sun's core, to crush tiny metal plates into plasma. The result, miniature seismic waves that mimic how energy ripples through a magnetar's crust, just scaled down to fit inside a warehouse. Then there's laser-driven starquake simulations. Facilities like the National Ignition Facility blast gold cylinders with 192 lasers simultaneously, producing shocks so intense they fracture synthetic materials in nanoseconds. It's like slamming a neutron star's surface with a cosmic hammer, except the hammer is 2 million joules of light, and the star is a target smaller than a pencil eraser. These experiments reveal how cracks propagate in ultra-dense matter, showing that even nanometer-scale defects can trigger system-wide failures when pressures cross a critical threshold. But perhaps the most eerie simulations happen in plasma chambers. At MIT's Alcator CMOD, researchers twist magnetic fields into knots resembling a magnetar's turmoil, then watch as the plasma snaps, releasing stored energy in bursts that mirror starquake flares. The scaled-down versions are 1 billion times less energetic, yet the physics is eerily parallel. Magnetic stress builds until it ruptures, spraying particles like a cosmic version of a shaken soda bottle exploding. Why go through all this trouble? Because lab quakes solve cosmic riddles. When the Z machine crushed tungsten into neutron star density plasma, it revealed that starquake vibrations might ring at frequencies we could detect with future telescopes. Laser experiments, meanwhile, suggest magnetar crusts could be weirder than imagined, not just brittle, but layered like a shattered mirror glued back together with cracks zigzagging unpredictably. The ultimate goal, to build a starquake forecast model. Just as geologists study laboratory quakes to predict tectonic disasters, astrophysicists use these experiments to decode patterns in real magnetar flares. One day, a lab's tiny plasma snap might explain why some stars scream on schedule while others detonate without warning. Until then, these machines offer something priceless, a front-row seat to physics so extreme it reshapes reality itself. Long before telescopes peeled back the night sky's secrets, humans watched the stars and wove stories from their tremors. Ancient Chinese astronomers recorded guest stars, sudden, blazing visitors to the heavens that faded within weeks. Today, we know these as supernovae, but what if some weren't explosions at all? What if our ancestors witnessed the aftermath of Starquakes magnetars screaming in X-rays so bright they burned into collective memory as omens, gods, or dragons? Take the legend of Fafnir, the Norse dragon whose death throes supposedly shook the earth. Medieval texts describe his writhing as the sky itself cracking open, accompanied by a light brighter than the sun. Modern astronomers note that a nearby magnetar, SGR 0501 plus 4516, had a violent eruption around the year 900, timing that overlaps with Fafnir's myth. Coincidence, perhaps, but when the Aboriginal peoples of Australia speak of Wandjina spirits painting the sky with fiery strokes after the stars trembled, it's hard not to wonder if ancestral eyes caught a magnetar's tantrum blazing across the southern sky. The Greeks feared Typhon, a monster so vast his head brushed the stars, his breath scorching crops. His battles with Zeus were said to light the heavens with unearthly flickers. Curiously, the Crab Nebula, a supernova remnant with a pulsar at its heart, became visible from Earth around the same era. Pulsars don't typically produce starquakes as violent as magnetars, but a major glitch in one could have briefly flared its brightness. Could Typhon's flickers have been a neutron star's seismic spasm, frozen in myth as divine combat? Even the Bible's book of Revelation describes stars falling, like figs from a shaken tree, a metaphor eerily fitting for a gamma-ray burst's afterglow, where magnetar flares can appear as descending ribbons of light. The Maya, meanwhile, tracked Venus with obsessive precision, yet their Dresden Codex also documents a star that bled fire before vanishing. Venus doesn't behave that way, but a Starquakes X-ray outburst might have been misinterpreted as the planet's wrath. These aren't just poetic accidents. Before science formalized the cosmos, humans relied on patterns, the kind that starquakes disrupt, a new light appearing where none belonged. A star pulsing erratically for nights before fading. These events didn't just inspire stories, they shaped civilizations. The Babylonians altered kings' coronations after evil stars flared. The Inca sacrificed llamas to placate angry constellations. Every culture had its own explanation, but the trigger might have been the same. A dying star's final screams echoing across centuries as warnings, prophecies, or celestial battles. Today, we've traded myth for math, but the awe remains. Those ancient sky cracks and star blood weren't mere fantasies. They were humanity's first attempts to describe the indescribable. Next time you hear an old tale about screaming stars, remember, the universe has always been louder than we imagined. Our ancestors just lacked the words to capture its fury. A magnetar's scream isn't just a spectacle, it's a death ray. Picture an exoplanet orbiting too close to one of these volatile stars, bathed in what seems like normal starlight until the star's crust fractures. In milliseconds, the planet's atmosphere is scoured away by a gamma-ray burst, its surface flash fried under X-rays hotter than a supernova. This isn't hypothetical. Astronomers estimate that a magnetar quake within 10 light-years of Earth could trigger a mass extinction, stripping our ozone layer and bombarding the surface with lethal radiation. For alien worlds nestled near neutron stars, the stakes are even higher. A single starquake might bleach a planet sterile, erasing eons of potential evolution in a cosmic blink. But destruction isn't the whole story. The same violent forces that rip atmospheres apart might also forge the building blocks of life. When a starquake tears through a neutron star's crust, it doesn't just release radiation, it hurls neutron-rich matter into space at relativistic speeds. These ejecta, packed with unstable atomic nuclei, could decay into heavy elements like gold, platinum, and uranium, materials essential for rocky planets and even life's molecular machinery. Some theories suggest that half the gold in the universe was born in the aftermath of neutron star collisions or quakes. Imagine a starquake as a cosmic alchemist, transmuting raw stellar matter into the very elements that might one day form an alien planet's mountains, oceans, or even the circuitry of distant civilizations. The paradox is striking. A planet too close to a magnetar is doomed, but in the galactic suburbs, starquakes might be life's silent benefactors. Consider a young solar system forming from a nebula enriched by ancient neutron star ejecta. Heavy elements forged in those stellar convulsions could coalesce into mineral-rich worlds, their cores warm with radioactive decay, a potential energy source for subterranean life. Or picture a frozen moon, its icy shell shielding an ocean teeming with extremophiles, while starquake synthesized metals in its bedrock catalyze biochemical reactions impossible on lighter element worlds. Timing adds another layer. A sterilizing quake early in a planet's history might reset the clock for life, but one that strikes later, after life gains a foothold, could accelerate evolution. Radiation shocks can drive mutations, and while most would be lethal, a handful might confer resilience, pushing biology toward complexity. It's a brutal crucible, but life on Earth has survived asteroid impacts and ice ages. On another world, could a starquake's aftermath be the catalyst for a leap toward intelligence? The wild card is distance. A planet in the habitable zone of a quiet neutron star, heated not by starlight but by tidal forces and radioactive decay, might enjoy stability for millennia, only to be obliterated by a single crustal rupture. Meanwhile, worlds farther out could reap the benefits of heavy elements without the fatal radiation. The difference between a cradle and a coffin might come down to orbital mechanics and sheer luck. For now, we're left with tantalizing what-ifs. No exoplanets have been confirmed orbiting neutron stars yet, but if they exist, their fate hinges on a brutal equation: proximity versus protection, destruction versus delivery. Starquakes might be the universe's way of giveth and taketh away, scorching some worlds barren while seeding others with the ingredients for something new. And if life does cling to existence on such a volatile frontier, it wouldn't just survive the storm, it'd be born from it. Could a nearby starquake actually threaten Earth? To answer that, let's turn to an astrophysicist who studies these violent cosmic events. Dr. Elena Rodriguez, a leading researcher at the International Space Science Institute, breaks it down. The good news is, the closest known magnetar is over 9,000 light-years away, far enough that even its most violent tantrums pose no direct danger. But hypothetically, if one lurked within 10 light-years, that's a different story. She explains the nightmare scenario. A magnetar's gamma-ray burst travels at light speed. You wouldn't see it coming. Within seconds, the blast would ionize our upper atmosphere, stripping ozone and triggering chemical reactions that produce nitrogen dioxide, a compound that blocks sunlight like a nuclear winter. Ecosystems would collapse, radiation levels would soar, and that's just from the initial flash. But here's the twist: distance isn't the only factor. Orientation matters, Dr. Rodriguez adds. Magnetar flares are directional, like cosmic laser beams. If Earth isn't in the firing line, even a close quake might miss us entirely. The real risk comes from undiscovered magnetars. We've only mapped about 30 in our galaxy, but statistically, there could be hundreds more hiding in dusty regions where X-rays don't reach us. When asked about historical near-misses, she points to 2004. SGR 180620's flare was 50,000 light-years away, yet it still briefly altered our ionosphere. If that had happened within a few hundred light years, we'd be studying its aftermath in ice cores and fossil records like we do with supernova radiation from millennia ago. So should we panic? Not yet, she laughs. The odds are astronomically low. But Starquakes remind us that space isn't empty or peaceful. It's a dynamic, sometimes violent arena where understanding these events isn't just about curiosity. It's about mapping the risks to our cosmic neighborhood. Her final thought lingers. We think of stars as timeless beacons, but magnetars prove they're living, convulsing objects. And sometimes they scream loud enough to remind us we're not just observers. We're participants in a galaxy that's far from quiet. Let's bring this cosmic violence to life. Picture a magnetar, its surface a swirling labyrinth of magnetic field lines glowing blue-white under unimaginable strain. The camera zooms in, revealing hairline fractures spiderwebbing across its crust, each one a ticking time bomb. Then a snap. A fault line gives way, not with the slow grind of tectonic plates, but with the instantaneous fury of glass shattering under a hammer. The crack races across the star's surface at half the speed of light, splitting the crust like a frozen lake in a quake. Now watch the magnetic chaos unfold. Those coiled field lines, trillions of times stronger than Earth's, recoil like snapped rubber bands, whipping the star's plasma into spirals of incandescent fury. The energy has to go somewhere. It surges upward, punching through the fractured crust in a geyser of X-rays and gamma rays. The beam narrows into a pencil-thin jet, hotter than a supernova's core, and rockets into space. From a distant vantage point, you'd see the star blink, a pulse of light so intense it outshines every other star in its galaxy for a fraction of a second. But the real spectacle happens beneath the surface. As the crust splits, vibrations dive deep into the star's core, where matter exists in a state beyond solid or liquid, a quantum soup of neutrons and quarks. The waves ricochet off this alien boundary, rebounding to the surface with amplified force. Ripples distort spacetime itself, creating gravitational echoes that, if we had sensitive enough instruments, might briefly stretch and compress every atom in our bodies from thousands of light years away. The aftermath is just as dramatic. The star's magnetic field, now scrambled by the quake, begins rewiring itself. Loops of plasma trapped in the newly tangled lines glow like neon spider silk as they reconnect. Some regions of the crust, now unshackled from magnetic tension, rise in kilometer-high ridges, mountains of ultra-dense matter weighing more than entire planets. Meanwhile, the jet of energy, now light years long, plows through nearby gas clouds, lighting them up like a cosmic flare gun in a fog bank. This isn't destruction. It's transformation. Every starquake leaves the magnetar forever altered. Its crust a little thinner, its magnetic field a little weaker, its spin a fraction slower. Like a phoenix burning itself down to ashes, these stars scream themselves into new states of being, and with each convulsion they broadcast a message. Even in the darkest corners of space, nothing stays still. The universe is alive with violence, and beauty is just chaos viewed from the right angle. Starquakes aren't just random cosmic tantrums, they're the universe's way of tuning its grandest instruments. Picture the cosmos as a colossal orchestra, where every star is a musician and every quake is a note in a symphony of extremes. Some stars hum softly, their vibrations barely a whisper, like the sun's gentle sunquakes. Others, like magnetars, are the percussionists of deep space, slamming their crusts with the force of 1 billion atomic bombs, sending shock waves that ripple through spacetime itself. Together, they form a harmony of chaos and order, revealing secrets no telescope could see on its own. Think of it like this: when a violinist plucks a string, the sound tells you about the wood, the tension, even the air in the room. Starquakes work the same way. Every crack in a neutron star's crust, every snap of a magnetic field, sends vibrations ringing through the star's interior. Astronomers decode these tremors like cosmic musicologists, listening for hints about what lies beneath superfluids swirling like liquid diamonds, cores of quark matter, or mountains of ultra-dense material no taller than a pencil but heavier than Everest. Each quake is a note in a song written in gravity's handwriting, and we're just learning how to read the sheet music. This symphony isn't just beautiful. It's revolutionary. Before Starquakes, neutron stars were static dots on a star chart. Now we know they're alive, writhing, cracking, and rearranging themselves in real time. They're not corpses of dead stars, they're laboratories for physics we can't replicate, teachers showing us how matter behaves when gravity wins. And like any great performance, the encore is unpredictable. A magnetar might flare tomorrow, rewriting what we know about magnetic fields. A pulsar's glitch could unveil quantum mysteries hiding in its core. So here's the real magic. Every time a star screams, it's not just destruction. It's an invitation to look deeper, to stay curious, to remember that the universe is louder and wilder than we ever imagined. The cosmic orchestra never stops playing. We just need to keep listening. If these stellar symphonies have left you hungry for more space mysteries, hit subscribe. The universe has plenty of encores left, and you won't want to miss a single note. And that's the universe's most violent tantrum, stars screaming through the fabric of space, cracking under cosmic pressure, and rewriting the rules of physics in the process. But this conversation doesn't end here. What's your favorite starquake fact? The way magnetars twist spacetime like taffy, how pulsar glitches could hide quantum secrets in their cores. Or maybe it's the eerie thought that we're all just cosmic bystanders waiting for the next stellar scream to light up the sky. Drop your pick in the comments or hit me with a topic you'd love to unravel next. Black holes that sing, time warps hiding in plain sight. The cosmos is full of mysteries and your curiosity fuels the hunt. Oh, and a pro tip from your friendly neighborhood space nerd. Consider this your official reminder to pack cosmic earplugs. Because somewhere out there, a magnetar's crust is tightening like a coiled spring, and when it snaps, the universe won't just whisper, it'll roar. Until then, keep looking up. The stars might be silent tonight, but trust me, they're always one quake away from stealing the show. If these stellar sound waves left you buzzing, don't let the adventure stop here. Smash that subscribe button to join the next cosmic deep dive. After all, the universe doesn't do encores, it just keeps screaming, and you won't want to miss a single note.